Deep neural networks rely on activation functions to introduce nonlinearity, but traditional functions like sigmoid and tanh have been largely replaced by more efficient alternatives like ReLU. However, ReLU shuts down negative values, leading to the development of variants like leaky ReLU and parametric ReLU, PRELU. Recent activation functions, such as Gaussian error linear unit, GELU, and sigmoid linear unit, CAReLU, have been widely adopted in natural language processing. Most activation functions process negative and positive values differently, implying that positive values are more important. But from a signal processing perspective, both positive and negative values are equally important and should compete for activation. This insight motivates the development of a novel competition-based adaptive ReLU, CAReLU, activation function, which scales input values based on the competition between positive and negative values. CAReLU defines two trainable parameters to adjust the scaling strategy and can be trained uniformly with other network parameters. The competition-based approach utilizes the interaction between positive and negative values to adaptively scale the input, enabling CAReLU to cooperate with different competition indicators to generate distinct activation functions for various tasks. Experiments on image classification, super resolution, and natural language processing tasks demonstrate the effectiveness of CAReLU, outperforming other widely used activation functions. Notably, replacing ReLU in ResNet 18 with CAReLU improves classification accuracy on the CIFAR 100 dataset. By acknowledging the equal importance of both positive and negative values and enabling them to compete for activation, CAReLU offers a promising activation function for a wide range of applications. The authors propose a novel method for constructing a competition-based adaptive ReLU, CAReLU, activation function. This method is based on the idea that both positive and negative values are equally important and should compete for activation, indicated by energy. The competitor with higher energy wins the qualification for activation. The authors define the percentage of positive values energy, pay, and use a sign function to determine whether positive or negative values win the competition. However, they note that this vanilla version does not perform well due to two issues. Lack of degeneracy into regular ReLU when prioritizing higher energy impairs performance, and discontinuities in the model's parameter space caused by the sign function. To address these issues, the authors introduce trainable parameters alpha and beta per layer, replacing the fixed scaling factor of 2 and bias of 1 in the sign function. They also replace the sign function with the tanh function to create a smooth version of the sign function. The authors experiment with other indicators for competition, including the percentage of positive values L1 norm, place 1, and the percentage of the number of positive values, PC. They define a competition-based adaptive scaling, CAS, function that adaptively scales the input based on competition results and constructs CAReLU by concatenating CAS and ReLU. The authors also discuss working with batch normalization, BN, which is widely used in convolutional neural networks. They define a BN CAReLU function that places CAS before BN to improve compatibility. The gradients of the competition-based adaptive scaling are derived from the chain rule, with initial values for alpha, beta, and k set to ensure that the CAS starts as an identity mapping at the beginning of training. Competition-based adaptive ReLU, CAReLU, is a novel activation function designed to enhance the performance of deep neural networks. The authors derive the gradients of CAReLU with respect to the input, a crucial step for gradient descent and backpropagation. By ignoring the small positive constant value epsilon and applying the chain rule to the differentiable components of CAReLU, they obtain the gradients. In experimental evaluations, CAReLU is applied to various applications, including image classification on the CIFAR 100 dataset and image super resolution on the Berkeley segmentation dataset, $300 Bahamian. For image classification, CAReLU replaces existing activation functions in every layer, utilizing three implementations: CAReLUE, CAReLUL1, and CAReLUC. The results show that most CAReLU implementations outperform baseline methods, with energy-based implementations generally performing better. An analysis of the values of tanh, alpha p plus beta, in CAReLU reveals that they do not generate significantly different values for different samples. Instead, input values are scaled uniformly and then fine-tuned for each sample according to the input's competition results. This allows CAReLU to utilize competition results without compromising performance when the original approach is optimal. In the $300 Bahamian image super-resolution experiment, an efficient sub-pixel convolutional neural network, ESPCN, is used to compare CAReLU with other popular activation functions. The results demonstrate the effectiveness of CAReLU in this task. The experiments validate the assumption that CAReLU can improve the performance of deep neural networks in various applications. The findings suggest that CAReLU can be a valuable tool for deep learning researchers and practitioners. Please provide the original transcript that needs refinement. I'll transform it into a concise, technically accurate summary suitable for voiceover narration, following the guidelines you provided.